Hi there, my name is Nicholas Long. I am with the National Renewable Energy Laboratory, and today I'll be presenting on our template-based district thermal energy system model built with Modelica, and this is part of the broader URBANopt project. There are many people that were involved in this, so thanks to the other NREL people. We have Amy Allen, Hagar Alarga, Nathan Moore, Brian Ball, Lauren Clune, Ben Pauley. From the Lawrence Berkeley side, Michael Vetter and Antoine Gauthier. From the CU Boulder side, Wang Dozuo, Katie Hinkleman, and Jing Wang. And then from Devontree, Ted Summer. So thanks everybody for your contributions. So let's start with motivation. Why does this matter? First, in the United States, district heating and cooling is somewhat a slow uptake as it is in other parts of the world. What you'll see here is the potential of district heating only, not district cooling, across the U.S. by state. So if you look at something as New York, you'll see the blue bar is 564 gigawatt hours per kilometer squared per year. That is a metric based on the population density and likelihood of district heating being effective. And you can see the red bar in there is that 71% is the district heating share currently. But some of these other states, you can see we're hovering around 15 to 50% of the potential. We're not only interested in district heating, we also care about cooling. Cooling is definitely newer, last, let's say 40 years maybe is when district cooling has been a thing. The way that we talk about that is through these generations of district heating and cooling. So first generation was steam-based, so very hot water, well, steam, and then you started to lower that temperature and prefab stuff started happening. And then fourth generation, you have much lower temperatures, around 50 to 60 degrees Celsius, still on just on the heating side. Efficiency was way up though, because now you're not heating water up as hot as before. Your losses are less. And then what we're really interested in is modeling what are called these fifth generation systems. They have lots of different names, ambient loop systems sometimes called. And this is where you get water at near outdoor ambient temperature. So between, let's say, 15 and 25, maybe 20 to 25 degrees Celsius. And so what's nice about those systems is that all of a sudden your buildings can supplement the heating or cooling as needed by a localized heat pump. And so here in this image, you'll see the heat pumps being attached to each of these buildings to either increase or lower the temperature that is needed for the system in that building. The advantage also is that you have more temperate water available, so waste heat is now is more attractive to systems that originally wouldn't be rejecting waste heat into into a district system. So a condenser of a refrigeration system now can dump its heat in there, or a waste water treatment plant can dump its heat into there because low-grade heat is actually of use. With that said, the little tidbit that we have, since we're close to Denver, Boulder is about 30 miles northwest of Denver, is that Denver has the oldest continuous operating district heating system in the U.S. It was about 1880 it was created and used, and you can see that they added district cooling in August of 1998. They had about 75,000 ton hours. Did hear though that they will be decommissioning the district heating. I don't know if that's just true. It was an article I read. We'll see where that goes. So great. Let's talk about URBANopt and this district energy systems work. Great. So URBANopt is one of the backbones of this, or at least the name and some of the models that we're using come from URBANopt. So URBANopt is a software development project that is led by the National Renewable Energy Lab. And it uses OpenStudio and Energy Plus as its main engines for doing the analysis. It's important to note that it is just a software development kit. It is not an end-user tool. It does not have any user interfaces other than what's in the command line or what you can program to. But what it does have is this modularity where you can connect via model exchange, data exchange style, to other entities or tools such as REOPT or OpenDSS for grid analysis, or these RNM models. And there's several of these things, right? And so each simulation can go off, run its model, and then return everything. We learned early on that that the district heating and cooling functionality was not going to be modeled to the, I guess, specificity that we would want to have. And that's kind of why we went down the, well, how do we add Modelica to this whole framework? And we'll talk about that, obviously, in subsequent slides. We're working with commercial software developers, specifically Ladybug Tools, to help implement some of the user interfaces. They're doing the work. We're just supporting them. And then if you have any questions, look at docs.urbanopt.net. So yeah, so in order for us to get from URBANopt all the way to the Modelica world, we created a project called the GeoJSON to Modelica Translator. It has now been acronymized into GMT over and over again. It's a lot faster to say. So if you hear me say GMT, that's what I'm referring to. It's open source, BSD3 clause. It's Python based, and it has two dependencies. One is on the teaser project out of Aachen, Germany, RWTH, and then the Modelica Buildings library, of course. There's a source code. We have a test suite that you can look at. It's all run on Travis CI, and we run everything with JModelica, and we test in Dymola. So what does it look like? I mean, the simplest, highest level I can give you is the bottom left is what you get from URBANopt, the SDK, where it generates a GeoJSON file. So however you generate that GeoJSON file, as long as you've defined the fields right, such as we need to know the year built, we need to know the floor area, we need to know the floor heights, we need to know the number of stories, we need to know the building type, things like that. We take that information and we augment it with the system design parameters data. So this is, I need to know what kind of boilers you have in your central plant. I need to know how do you want to model your ETS. That's the energy transfer station. That is the energy that goes from the network to the building, right? So in this case, it's indirect cooling. And then that gets exported to Modelica. It's a command line tool currently. It's actually a Python package. And then if you want to run it, you run it as a command line tool. So what does it look like? And the four blocks that matter are these. You have a district plant, you have the network configuration, you have the ETS and the loads, all the energy flows typically, out and back in. And then you blow up that box and you see this. So we learned real early on that we wanted to be able to handle defining the building loads in various ways. So we looked at originally looked at just doing RC models, and we found teaser, and then we decided that teaser was going to be probably the best approach for us because we can take high level data and have it generate RC coefficients for us and export the Modelica files that work with the Modelica Buildings library, and that was nice and smooth, and we didn't have to worry about it. But we also want a time series, so we can just throw a load at it, or we can throw an m.delta-t at it. And we also wanted to leverage Spawn of Energy Plus, and that's how ultimately we're going to make the connection of URBANopt SDK, which is all Open Studio Energy Plus based, into this world where those models now become or get consumed by the GMT, the GeoJSON to Modelica translator. We wanted to have flexibility with the energy transfer stations, so definitions of the heat exchangers, the pumps, the water heat pumps, so indirect, direct. We wanted flexibility in the brown side, which is the network configuration. Is it one pipe or a 4-pipe system? And then last, we want to be able to have flexibility around the primary equipment or the central plant, right? Or the district plant, rather. So kinds of boilers and cooling towers and chillers, things like that. The idea is to make this as drag and droppable as available. So I'm going to go through 4 types of loads rather quickly here, but 4 different ways of modeling the building loads. Teaser, as already mentioned, exports to the RC models that we care about. So here's the teaser model. This is us coupling it on the right-hand side to an indirect cooling ETS with infinite supply side for heating and cooling. Fine. But one thing we had to do was do some tweaks. And so the tweaks, we had to add in like a heat port, which up here. We had to add in the T-air. We wanted to model the latent loads. And so all these little tweaks happened after they got exported from teaser. And so the way we did that was with a library that we built called the Modelica Builder. And I'll talk about that, but in short, it's a way of changing or updating Modelica files using Python. And it's not just doing string replacements. It's understanding the full context of the Modelica file and changing things with context. So the second way of doing loads is with Spawn of Energy Plus. This is each thermal zone becomes a connection to the terminal unit inside of this partial building, which was developed by LBL. Here you'll see that there's 6 thermal zones. Really, we only care about 5 of them. The 6th one is the attic, which I'll show you why that matters later. And then again, same right-hand side where we're coupling it to an ETS, a cooling ETS. Third way is just building loads. So want to know how many kilowatts per time step. So the combi table here is all that matters. Same coupling on the right-hand side. But we had to pre-compute a bunch of loads. So we did that for about 1,200 reference models in the US, and those are available here at this link. And it's for all the major building types across the major climate zones. If you want to add more, they're all actually the models or the scripts to run the models are in that same link. And then lastly, same idea is these m.delta T style loads. And this is a nice way of modeling from OpenStudio's vast selection of HVAC systems. There's like over 100 of them that you can simply say, I want this type of system, and it'll create it for you. So now this gives us access to modeling various types of HVAC systems using something as simple as an m.delta T, assuming that it's water-based, of course. The example over here is connected to a heating and cooling indirect energy transfer stations, and then it's connected to infinite sources. Great. Now let's look at the district side of things. So now we're top right. You'll see we're kind of focusing more on ETS connections to the district loops to the plants. So what you're seeing here is our capabilities, I guess, for the cooling and heating plants. We can do 1st generation district heating, 4th generation district heating and cooling. We're working on the 5th generation district heating and cooling piece of this. For the most part, we're vectorizing everything that we can, so the boilers and the chillers will scale out as needed to meet the load. That has been somewhat of a challenge, is to handle this load, or auto sizing, if you will. So here in the diagram, you got the top right is the cooling plant fed to the distribution network. So this is your piping. There's actually 8 spawn buildings in here. This is vectorized as well. We're just fixing a heating source for now, but the cooling plant, you can see down below, and then the cooling towers. Here's the district cooling example that I'm going to kind of delve into just a little bit here. Same idea. We have 8 buildings with an indirect cooling ETS. Inside of that, you see there's district cooling network, district plant, and then the spawn template, which you saw before. And then what does the indirect cooling look like? Well, there you go. Great. So fantastic. Now you create a GeoJSON file. You've specified your system's parameter. What type of ETS is it? What type of chiller is it? What's the set points, things like that. Then you, via the command line, have it export the Modelica project, and then you run that in JModelica or open it in Dymola, and this is what your results would look like, right? So all the 8 buildings have the same temperature. They were all identical. Here's the cooling loads for July. And then remember, we only cared about 5 of the zones. The 6th one was the attic, and just verifying that the attic temperatures were floating. Looks good. On the evaporator side, the condenser side of the plant, you can see that the systems responded, as expected. So, that was a lot of magic to even show those 2 slides there of how the results of the district cooling system look. The heating systems look similar. However, there's some work to be done, right? The ease of implementation and flexibility can be rigid, and you'll know it when you hit it, that it just doesn't do what you want it to do. So working on that, we do need to have some tighter integration with the URBANopt SDK project and OpenStudio and Energy Plus. But the big part of the work is going to be around adding energy conservation measures for Modelica, GeoJSON, and FMUs. The work for the pilot project is also happening, and that's going to be focused on a 4th generation system. So with the last minute that I have, there's 2 things I wanted to hit. One was this Modelica formatter. The idea is that we can dynamically fix the formatting of Modelica files using this thing called Modelica FMT. 3,700 files in about 2 minutes, cleaned up, fixed, goes from this format to this format. This makes diffing of files much easier. This makes resolving conflicts via Git or Mercurial, whatever you're using. It just makes it so much easier. Highly recommend everyone adopt something like this. If not, here's the details of adopting this exactly. You can integrate it into pre-commit, and it just makes life easier. We just learned that as we were developing that we were spending a lot of time formatting Modelica files and dealing with conflicts that we didn't need to. Second thing is the Modelica builder, which I mentioned in the teaser world. And the idea there is that if you have an existing Modelica file that you need to manipulate programmatically, you can open or you can import this Python package called Modelica builder, and it will give you access via the abstract syntax tree grammar, so the AST grammar. And in context, you can do things like removing components, adding components, changing initialization values, removing connectors, things like that. And so you can see that's how we added the, for instance, the TR variable into our teaser model. Example, this is where it lives. It's all open source as well. But here's an example of what it would do. You load the model. You can say update argument of, with the resistor to 55, and then you hit save, and there you go. It writes it back out as 55. So this combined with the Modelica FMT is just a powerful suite of tools that we're using to kind of bend Modelica to where we need it to be to make this templating and development of the district energy systems feasible. So with that said, I'm at my time. Thanks for listening and watching, everybody. I've listed 4 contacts on here. This is kind of the 4 contacts from the various labs, and then I added the Devitree as well, who worked on the Modelica FMT and the Modelica Builder world. Anyway, so contact us via email, and I'm happy to answer questions if you have any. Stay safe, everybody. Thanks.